Okay, so new topic. We're going to talk a little bit about data streams. I'm not sure how far I will get by 5:30, but there are a number of interesting algorithms that assume the data comes in a stream. The characteristics of streams are, first of all, typically very fast. You talk about things like the search queries coming into Google, or petabyte a day of data coming down from a satellite, sometimes you need your own algorithms or specialized algorithms to deal with data that's coming in that fast, and some of the algorithms, in fact, even make a lot of sense if your data is sort of ordinary database data as well. In the first of these two slide sets, I want to just introduce the stream data model, say a little bit about it, then the notion of sliding windows, which turns out to be very important in describing what it is you can do with a data stream, and then talk about a particular algorithm for counting ones in a bit stream. And well, let's see. Okay, so the key difference between data as a database person sees it and the data as a stream management system or person sees it is that in a database system you control how the rate at which data moves and how it comes into your database system. When you have a stream, the rate is not under your control. Google has to handle every search query that comes in when it comes in, no matter how many people are searching at the same time. If you're Amazon, you have to deal with, people want to buy stuff, they click. You don't control that. You have to deal with as many clicks and requests as come in at the time. So the stream data model, which is first of all, you have several input ports, often many input ports. I'll assume that data elements are tuples, that is, records or vectors. They come in at these input ports. Again, you can't control the rate at which they occur. And we assume that the data is coming in so fast that you can't store all the data in a way that makes it easily accessible. Maybe you can store it in some kind of archival storage. I mean, that's sort of what these systems that handle satellite data, it's what's called write-only storage. Whatever comes in, you store it away on these big tertiary storage devices, and then nobody can ever see it again. Okay, but the algorithms that I want to talk about are really how can I say something useful about the stream? Doing it in a way, preferably in main memory, or at the very least using only a small amount of secondary storage, no tertiary or archival storage. Okay. Now, I also want to talk about, really, there are two query models. One is that I can ask ad hoc queries. That is, I ask a query in the sense of a query in the sense of querying a database, but I do it about the entire stream seen so far. So here's a simple example. At any given time, I might want to ask, what is the maximum value that I've seen so far on this stream? And now that's fairly easy to answer. What it means is I have to keep the maximum value stored separately, and that's only one. It's one value. It's a couple of bytes. Obviously, every time a stream element occurs, I need to update it, but that's probably okay. So I can probably do that. And then a standing query is something which sort of operates autonomously and asks you to basically to report on the stream at all times. So, for example, this query says, every time I see a value in the stream that's bigger than any previous value, that becomes an output. I have to spontaneously issue that as an output. So nobody's asking for that, or you ask for it once and it applies forever. The system has to just spit out the answer every time there is a new maximum value. And again, that is this query. It's not too hard to imagine how you would do that. Again, you keep the maximum value every time a new value comes in. If it's bigger than the previous maximum value, you not only change the maximum value, but you spit out the new value in the outputs. So here's the proof. You have a query management system. It stores standing queries. It can accept and answer ad hoc queries as well. There are many streams entering. It makes outputs occasionally, either in response to ad hoc queries or standing queries. And there's archival storage, which is large enough to store everything, but so large that you can't conveniently compute with it. You can only do that sort of offline. And then you've got some limited working storage, which might be a main memory, preferably as main memory, might be secondary memory. Okay. So again, there are lots of applications of this. For example, if a search engine like Google might want to know about trends, what queries are appearing more frequently today than yesterday. An interesting application, which is actually was used by Yahoo in practice, is they wanted to know about pages of theirs that are being clicked more frequently this hour than the previous hour. And the reason, well, sometimes that's because something has happened and everybody needs to know about Justin Bieber or something like that. But the practical reason it was that you see this phenomenon whenever a link gets broken. People click on the page many times before they go away and realize that they're never going to get it. So you actually have a big spike in the number of clicks on the page. And so that actually helps Yahoo to find and fix broken pages without having somebody having to look at all million or so pages that they put out. You can say IP packets are streams. Again, a switch is a number of streams coming in, number of streams going out. And the kinds of things you might want to do is to find out where packets are headed, so you have some idea of where the delays in the network might be, or if you notice that there are all of a sudden a lot of packets headed for one address, that could be a denial of service attack, and you'd want to intercept that in the middle of the internet rather than delivering it to the edge. And so, people who study these things have pretty much convinced that the only sensible way to ask most queries about a stream is to imagine that you have a window. Typically, it's got a fixed length. That is, you ask something about the last n inputs on a stream. Sometimes you might say the window might be time delimited, so all the inputs received in the previous hour. But the idea is that you just can't go back forever in the history of the stream. You have to keep focusing on the last so much of the stream. Again, typically it's all archived, so in principle, if you have to go back 2 years, you can do that. You just can't do it online. You can't do it as a standing query or reasonably as an ad hoc query. Okay, now a lot of the algorithms that are worth talking about for streams are those where the window is finite, but it's so large you can't store it in main memory. So you'd like to do something simple to sort of summarize the window in a way that still lets you answer a certain class of queries, but maybe not every query. Now, these days you have so much main memory. I mean, windows can be enormous, but in many of these applications, you actually have many different streams. And if you've got a million streams and you want to keep a window for each stream in main memory, then the windows all of a sudden can't be very big. Or you have to summarize the windows in some way, and that's what we're really going to concentrate on is summarizing them. So this I don't know if this picture is useful or not, but here's a stream coming in. Window is the last 6 characters. So at some time it contains S, D, F, G, H, J. Now the next element K comes in. The last element S falls out of the window and is no longer part of the window, so you can see what the window now contains D, F, G, H, J, K. Then the next element L comes in, D falls out, and so on. Okay. So at any time, the window consists of the last 6 characters that I've seen. Okay. I'm sorry.
So, I want to ask, why to use this window model rather than just processing the stream, like single tuple at a time? What is the benefit we get out of this?
Well, again, it's a question of you can't just process the whole stream. You can't ask questions. The stream is coming in so fast. You can't just store all the tuples and make them all accessible at the same time. Okay.
So I'm asking about window of size 1. So if you are doing single action on a tuple and then maintaining a model or updating a model with single tuple.
No, remember, if a window of size 1 says, all I ever care about is the most recent tuple. And I'll never ask anything that doesn't pertain to only that one silly little tuple.
Okay.
And you don't get anything interesting when you do that. You get more interesting things if your window is, say, length 1 billion. So you want to know how many of the last billion, let's say, again, think of it as click streams. You want to know how many, you keep the last billion clicks, and I want to know which URLs have been clicked twice as frequently in the most recent 500 million as in the half a billion before that? That's the kind of question I want to ask. But if you keep the whole thing, and you want to ask, let's say, how many, what URLs have been clicked more in the last half than in the first half? First of all, the halves get bigger and bigger as time goes on, and the question no longer is really interesting, because it's, after 2 years, you're asking how many, which URLs were clicked more frequently this year than last year. Not interesting anyway. But moreover, then you just have so much data that it becomes harder and harder to answer any query like that. So that's sort of why it makes sense in many situations to say, I'm going to pretend the stream of interest is only some reasonable number of inputs into the past. Anyway, maybe in fact this example might help a bit. Okay, so my stream is integers. I'm using a window of size n, and I'm going to say I want to know at any time what is the average of the integers in the window. Now, again, think about doing that. What is the average of the integers for the entire stream forever? That's a little bit trickier. It could be done. It's not that hard, but also becomes sort of less meaningful as time goes on, because after a while you're just the average is dominated by stuff that that came in 2 years ago and may have no relevance today. Okay, so what's the average of the integers? Okay, for the first n inputs, you just do the sum and the count, and then one more step at each input, you get the average. So it's really just for each input you're doing 3 arithmetic steps: one to add 1 to the count, another to add the input element to the sum, and then another one to do the division. Okay, so that's sort of doable, right? The work is just a constant per input. Now, after you've got your first n inputs, now the window begins to slide, and what you need to do is okay, say I is the next input. Now, the oldest input that's in the window is going to fall out of the window. So let's say that that's J. So you're adding I, and you're subtracting J from the sum. The count doesn't change. So if you think about it, to get the average, you can update the average by simply taking I minus J, dividing it by n, and adding that to the previous average, and that gives you sort of the increment in the average. Okay, so that's not that hard. And again, it's just 3 arithmetic steps per input. Okay, should be feasible. Okay, so again, that's fairly cool, because it says the amount of work we do per input is probably dominated by the protocol that actually accepts an input and puts it in some buffer to be processed. Anyway, so order n time per input is always good, but the bad thing is it requires the entire window be stored as is. And again, if n is a billion, well, you can store a billion integers in main memory these days. Not such a big deal. But again, what if n is a trillion? You can't store that in main memory. Or if n is a million, but you have a million streams and you want to keep the average on each of those streams. So you might have some problems. And in fact, for this particular query, there really is nothing you can do if you want the exact answer. Okay, so what I want to talk about is an example of an approximate algorithm. The goal of this algorithm is to count the ones in a binary stream, and it uses much less space than the length of the window, and what you pay for that is that you don't get an exact answer. What I will describe to you gives you an answer that is off by no more than 50%. There is a better algorithm that is off by at most epsilon. You make epsilon as as small as you like except 0. And it still takes the same running time to within an order of magnitude. That is running time per input. And by the way, counting the number of ones in a window suffers from the same problem as computing the average of a stream of integers. You can't get the exact answer unless you keep the window itself. Okay, so if you want to, you'd really need n bits to store a window of size n. If you want to always be able to know how many ones are in the window. Okay, so we're going to do something that seems a little bit more complex than just counting the number of ones in the window. We want to be set up to answer the question, how many, I can at any time query, say, how many ones are there in the most recent k bits, where k is anything up to the window length. Okay, and again, I can't get an exact answer. I will always get an answer within 50%. Okay, so again, certainly if I store the most recent n bits, I can at least answer the question. Of course, since k is an input parameter to the query, it's going to take me time k to count up, to look at the last k bits and find the answer. So that's not even that's not that great. And so even if I had enough room to store all the bits, answering the query efficiently can't really do it. And again, as I've said, a billion bits, no problem storing it in main memory. But if you have millions of streams and you want even a million as the length of your window, you're not going to be able to do that in main memory. So just to give you an example of where this might make sense, again, you might have a site in which with lots of pages, and every time there's a request for one of those pages, you want to log it and you want to know how many, in the last k requests, how many of these. For each of your pages, you want to know how many times in the last k requests was that page requested. So technically, you've got one stream, which is a sequence of URLs. Let's say we want to keep the last billion requests. You can convert this into a large number of streams, but the streams are binary. Okay, so what I want to think now of, there's a binary stream for each URL, and again, the position has a 1 if that URL was the one requested, and it's 0 if some other URL was requested. Okay. Now I want to talk about an algorithm called I call it DGIM. It was named after, these are 4 of my colleagues listed here. And the interesting thing is it can maintain windows of length n, but it only has to store log squared n bits per stream. And again, if n is a billion, log base 2 of n is 30. 30 squared is 900. 900 bits is a lot better than a billion. Well, of course, there's a constant factor that's hidden by the big O, but it's still a lot better for numbers of that scale. But as I said, it will give you an approximate answer. Again, in the version I give you, it can be off by as much as 50%, but you can improve that down to anything greater than 0. If you still be order log squared n bits, but the constant factor would grows inversely inversely with the epsilon that you want to be the maximum error factor. Okay. Now the algorithm, okay, there's a notion of timestamp. Okay, that is each input that comes in, the first input that ever comes into the stream will have timestamp 0, the next one will have 1, 2, and so on. However, since the window is of length n, anything in the history beyond n, we can completely forget about that. We'll never care about that again. So as a result, you can record your timestamps modulo n. And what that means is that all your timestamps can be represented by log base 2 of n bits. Now there's this concept called a bucket, and what we're going to do is we're going to break the stream up into segments. Each segment will have a number of ones, which is a power of 2, and there'll be certain rules for how many ones can be in a bucket. But what we're going to represent the stream by is not the actual bits, but the buckets of which it is comprised. And by the way, no stream of length n will ever need more than about 2 log base 2 of n buckets. Okay, so the bucket then will consist of the timestamp of its end, and that again was modulo n, so it's going to be log n bits. And the number of ones between the beginning and the end of the bucket. Okay. And by the way, the number of ones in a bucket is always a power of 2, and therefore you can represent the number of the number of ones in a bucket by the power of 2. So since no bucket can be longer than n, log n bits will suffice to represent the size of a bucket, that is the number of ones that it contains. Although it doesn't really matter because we're already spending log n bits representing the timestamp, so that dominates the cost of representing a bucket. Okay, now let's see, there are rules. A stream will have either 1 or 2 buckets with a given power of 2 number of ones up to some maximum. Okay. The buckets, the territory of the bit stream that are represented by a bucket, they don't overlap. So the stream is divided into disjoint buckets. Zeros don't count, so there might be some zeros that are not part of any bucket. That doesn't really matter. Now, one of the big tricks is you want to sort the buckets by size so that the recent buckets are little. You know, there'll be 1 or 2 buckets of size 1, that is a single 1, and those will be the most recent. And then there'll be 1 or 2 buckets of size 2, and those will be next most recent. And then there'll be 1 or 2 buckets of size 4, which are a little older. And then 1 or 2 buckets of size 8, which are still older than that. And then all the way up to as many buckets as you need to represent the n bits. No bucket, of course, will have more than log n 1, will require, sorry, there can't be more than 2 log base 2 of n buckets, because there are at most n ones. And if you think about it, since the sizes of the buckets are growing exponentially, within log n, within 2 log n buckets, you get to a bucket whose size is already n, and that's going to cover everything in the window. Now, again, every bucket records its end time. Once the end time falls out of the window, you just drop it. It's no longer part of the representation. Okay, so here's well, this is not because PowerPoint has sort of a discrete grid that you don't normally notice. It's things are a little bit off, but here's a stream. This is the most recent bit to 0, and this is going back in time. We have two buckets of size 1. The first one is this one. The second one is that one. Then we have 1 bucket of size 2, which consists of this 101 here. And then you've got 2 buckets of size 4. There's 1100101 is one of them, and then previous to that we have 1010101. And then here's a bucket of size 8, another bucket of size 8. Here's a bucket of size 16, and that's already partially outside the window. Okay, and so any previous bucket will have its end time prior to the n most recent inputs. So that's gone. We no longer have any record of any buckets outside that. Okay, so everybody have a feel for what the buckets look like? Now, a new bit comes in. Okay, first of all, if the end time of the oldest bucket is equal to modulo n equal to the time of the current input, that means that it's n, it's more than n, or it's n plus 1 time units ago. So we drop it. Okay, and that's why we only need to calculate times modulo n. Now, if the current bit's 0, that's the end. That's all we need to do. The buckets then stay the same, because the interesting thing is what happens when the current bit is a 1. Well, first of all, we're going to create a bucket with just that 1. That is, it will have the timestamp. The end timestamp is the current time, and the log of the size is 0. Okay, it's a size 1. The trouble is, if I had 2 buckets of size 1, now I have 3 buckets of size 1, and that's illegal. So what do? I take the 2 oldest buckets of size 1, and I turn them into a bucket of size 2. And I can do that by simply forgetting about the third of the oldest, the oldest of the 3. Its end timestamp doesn't matter anymore. The end time of that bucket of size 2 is the end time of the second oldest of the 1s, but I raise its size so that instead of 1, it's now of size 2. Of course, now, having created a new bucket of size 2, I may now have 3 buckets of size 2, and that's not legal, so I have to take the 2 oldest 2s and turn them into a 4. And of course that can create 3 4s, so I have to create an 8 from 2 of them, and that may create 3 8s and so on. But it can't ripple more than log n time because, again, because there can't be buckets that big, bigger than size n. So this is the example stream that I gave you. And here are the current buckets. Now, suppose a 1 comes in. Oops. Okay, so I've created a new bucket of size 1, and oops, now I have 3 buckets of size 1. That's not good. So these 2 guys are going to get combined into a bucket of size 2. And that's been done here. And that's all I need to do because I only had 1 bucket of size 2. Now, suppose that in the next 3 bits to come in are 1 0 1. So this is what I've created for the 1. The first one that comes in, I create a bucket of size 1. That's okay. That just gave me 2 buckets of size 1. 0 came in, I didn't do anything. 1 comes in, I create the 3rd bucket of size 1. Now these 2 are going to have to be combined into a bucket of size 2. Now I've got 3 buckets of size 2, so I combine the oldest 2 into a bucket of size 4. And you can see what happens. It's going to ripple, right? I've now got 3 buckets of size 4, so I combine the oldest 2 into an 8. That gives me 3 8s, so I combine the oldest 2 8s into a 16. And I guess I'm okay because I only have 2 buckets of size 16. Okay. And so in the worst case, it could take me time, order log n, to do all the rippling and fix up the bucket sizes. On average, of course, it's going to be constant. Okay, most additions of a bucket of size 1 will not ripple very far. Okay, so you have, in the extreme case, 1 input comes in, you might take order log n time. On average, it will be order 1. Now, given that I'm representing things by buckets, how do I estimate, how do I answer the query? How many 1s are there in the most recent k bits for some value k? Well, first of all, I'm going to only look at the buckets that are of whose n timestamp is within k of the current time, right? Because anything else it can't possibly contribute to the last k bits. And again, this is going to take me all the time, order log n, to sort these things out, to figure out or to estimate how many 1s there are. Remember, I don't know exactly how many 1s there are because the old 1s have been collapsed into a bucket. The bucket covers some territory, but I don't know how many, are the 1s heavy at the recent end or at the oldest end, or how are they? How do they actually sort out? So I'm never going to be able to recover exactly where the 1s are in the territory represented by the bucket. But I do know this: of all of the buckets that are not the oldest, they begin within the last k time, within the last k inputs. Therefore, all of their 1s count toward the answer to the query. So I'll just add those, and then I've got this oldest bucket. I don't know how many of its 1s are within the k, so I'll just take a shot. I'll say half of them are in, and half of them are out. Okay. Now, how bad could that be? So suppose that the oldest bucket has 2 to the I, is of size 2 to the I. Now, I know at least one of the ones is within the last K, because otherwise the whole window, the whole bucket would be outside of the range of the last K, and therefore I wouldn't even be looking at it. At most, all 2 to the I might be within the window, not within the window, within the last K. So my error is at most 2 to the I minus 1. Okay. I say 2 to the I minus 1 are there. It could be as little as 1 or as many as 2 to the I. So it's certainly no worse than off by 2 to the I minus 1. However, since there is a bucket of size 2 to the I, there's also at least one bucket of size 2 to the I minus 1, and at least one bucket of size 2 to the I minus 2, and so on, down to of size 1. And so, and since you also have at least one from the oldest bucket, the true sum, the true answer to the query can't be less than 2 to the I. Okay, so I've made an error of at most half the true sum. Okay, so I claim that the answer to any query can't be off by more than 50%, and usually is a lot better than that. Okay, because whenever there are 2 buckets of size 2 to the I minus 1, already you get a third would be the maximum error, and so on. Okay. Okay. So again, the book describes how you fix that up to make the error epsilon instead of a half. It's not too hard. Okay. So we have let's try. Let's see. This is all the material that I had prepared for today. Let's see. I actually finished 10 minutes early. Is anybody objecting?
What is the average error rate?
What?
What is the average error rate? The worst case is 50%, right? So what is the average case?
Well, let's see. We can figure out, assuming that the the probability is half of there being 1 and half of there being 2 buckets of any size. You can figure out the average size of the correct answer. The average, if you assume that the kth element can be anywhere within the last bucket with equal probability, so then the average error there would be half of the maximum, or it would be 2 to the I minus 2. So the average error is going to be, I'd like to say, about a third of the 50%, or about an average would be about a sixth, something like that. But again, that's making very specific, simplifying assumptions.
Another question, which is one counting of windows.
Mm-hmm.
Does it have any? Is it an abstraction of some application, or more to be extended to solve more realistic problems?
Yeah. Well, again, it does represent counting large occurrences. What your stream is really doing is like it's a URL stream,
Okay.
where what you want is an approximate count of the number of occurrences of each URL.
Exactly.
Okay, so
you
that's
still have to spread it.
right.
Yeah, but essentially you can do this
Yeah.
generalization. This is a distinct value counting, right?
Yeah.
Which is a very important application.
Yeah, actually, we're going to talk about I think tomorrow. The first thing I'm going to do is to count distinct.
Yeah, yeah.
Very key. It's my old colleague John Hopcroft and Ravi Kannan have come out with a competitor for the MMDS book. And there is one algorithm in both books, and that's Flageolet-Martin, okay, which we're going to talk about tomorrow. That's the only thing that we both agree on is important. And that's what Volcker said. It's counting counting the number of distinct elements in a stream without having to remember exactly what elements you've seen.
Exactly.
Mhm.
Very good.
Okay. So,
Thank you very much.
why don't we, thank you.